In the last lecture, we discussed Bode plots, and we are dealing with the basic building blocks of Bode plots, that is the real pole and the real zero. Today, we're going to expand that and include complex poles and zeros. This is slightly more complicated, but you will see that it's very similar to what we did in the last lecture. So by the end of this lecture, you should be able to, again, represent the phase and magnitude of a Bode plot, but at this time, using functions having complex poles and complex zeros. What we did in the last lecture was to represent phase and magnitude of a transfer function in a Bode plot. So we have a process g of s. When you give it a sinusoidal waveform, we get a sinusoidal waveform in the output. This sinusoidal waveform in the output will differ from with respect to the input in two ways. The first one is that the magnitude will be scaled, and that the scaling factor is the magnitude of the transfer function itself, that it depends on the real and imaginary part of the transfer function at a given frequency. And the second difference is the phase shift, that also depends on the phase and magnitude of the transfer function g of s, as we saw in the last lecture. What we do in a Bode plot is simply represent the phase and the magnitude change as the system is subjected to a sinusoidal input at a wide range of frequencies. And we do that using a log scale. So both the frequency and the magnitude of the transfer function are represented in a log scale. And the phase is typically represented in degrees. So because we are taking now log scale more specifically, we are looking at representing the transfer function gain in decibels. We are taking 20 log of the magnitude of this transfer function. And you remember that there is an interesting property with log, is that 20 log of AB times B is the same as 20 log of A plus 20 log of B, which means that if we now know the building blocks for things like poles and zeros, we can simply add everything together to create the Bode plot of the entire transfer function. For the phase, it is the same. We can simply add the phase of all zeros, subtract the phase of all poles, and that gives the phase of the entire transfer function at a given frequency. And that's what we represent with the Bode plot. So in the last lecture, we addressed real poles and real zeros. And the way we were doing the Bode plot was to first identify how many of these building blocks we have, draw the Bode plot for each individual building block, and then add them up. It works fine. It just takes a lot of time. So today, before we go into complex poles and zeros, let's do a quick exercise using a different method, which is not that different. Is that the only difference is that we are adding all the elements right away. We're not doing individual plots and then adding everything up. We are just going to do that at once with just one signal, and that will already represent the entire transfer function. So let's do a few examples. One example, two, if we have time, using this method. It's just faster, and then you don't need to bother with a transfer function that it has, like, let's say 3 poles and 3 zeros. You would need to draw 6 lines and then add everything up. It becomes quite messy. Let's do one exercise, and for this exercise, let's consider this transfer function, 10s plus 1. So this is not in the lecture notes, but there are some exercises in the past lecture that I solved using this method, and I only gave the final answer there. Let's see how exactly that was done. So let's consider this transfer function for now. If you were to do the Bode plot for this transfer function, what building blocks can we identify here?
There's 3 poles and 1 zero.
There are 3 poles, 1 zero, and there is a gain, right? A gain 10. So it would need to do 3, 4, 5 different plots and then add everything up. So that will become a bit messy. So let's see how we can do that differently, if we can. Give me 1 second. Okay, there you go. Okay, so here I have a generic Bode plot, and we're going to fill that up. So looking at this, we can see that we have a real gain, and the gain, as we saw in the last lecture, plot is just a constant line, and that will be added to the actual Bode plot. So we will affect it will affect the entire Bode plot at all frequencies. The gain will affect the Bode plot at all frequencies. A pole and a zero that are not at the origin will also affect the Bode plot, but they will only affect the Bode plot once we reach its crossover frequency. Right? For example, if you look at this pole here, we know that before that pole, before you reach that pole, the gain for this particular pole will be 0. And when you reach 0.1 radians per second, then it will start to decay by 20 decibels per decade. So before we reach that cutoff frequency, this pole does nothing. And same goes for this pole, and same goes for that 0. Once you reach a pole and the 0, we are adding a slope to the Bode plot of plus minus 20 decibels per decade. Which means that if you now look at this transfer function and you go to the low frequencies, all the way to the low frequencies, to the left of all these cutoff frequencies, what is the only thing acting on the Bode plot?
The gain?
Is only the gain, right? So if you go all the way here, before you reach all our cutoff frequencies, only the gain is doing something, which means that at the low frequencies, the Bode plot magnitude will simply be 20 log of that gain 10, which is 20 dB. And where does it start to change? If you are all the way at the low frequencies and we are now going towards the higher frequencies, where does it start to change magnitude? When you reach the first cutoff frequency, which is 0.1, that's the smallest one, 0.1 radians per second, that's here. So from a very small frequency tending to 0 up to 10 to the power of -1, we can say that the magnitude of the Bode plot is 20 dB. Is this clear? Yeah?
From the pole, how do you decide it's 10 to the -1 rads per second?
Yeah, so for the pole, we can see the cutoff frequency is right there. This is one cutoff frequency, this is another cutoff frequency, and S divided by 1 here is another cutoff frequency. All right, so these are all the cutoff frequencies, whatever divides S plus 1.
Okay.
Nice. So this is for that. So this is the first one, then you go to 1, that's a 0, and then you have a pole at 10.
So in this case, or in this kind of transfer function, we just need to start with the gain first. And
in this particular case, yes, because we have no poles at the origin, up to the first cutoff frequency, only the gain is acting, right? But if we had a pole or a 0 at the origin, it would be a little different. You can see that later.
The origin here means the 10 to the -3.
Now the origin, I mean 1 over S, or S, a pole or 0 at 0.
Oh, okay, I see.
At the origin of the S point. That's what I meant. Okay, so first we have here something that goes at 20 dB, and that stays at 20 dB up to the first cutoff frequency. If this gain wasn't here, if this was just a 1, what would be the gain here? Would it be 0, wouldn't it? It would be 0 like any other pole. The pole starts at 0, and then it starts to decay once you reach a cutoff frequency. So if this was just 1, 20 log of 1 is 0, it would be 0 up to the first cutoff frequency. Now we reached 10 to the power of -1, cutoff frequency of a pole. So this is a pole. What happens to the Bode plot? The slope changes, and the slope now becomes
-3.
Negative. Yes, so this slope right here, the magnitude would be -3 compared to what we have. So that's 20 minus 3 would be 17. And then it would start past that, it would start to decay by -20 decibels per decade. Okay. So for simplicity, let's forget about the -3 here because it shifts everything down later. but we can account for that later on. For now, let's just focus on the slope. But you're right, at this point, because it is a cutoff frequency, the magnitude would drop by 3 decibels and it would be 17 dB. All right, but let's assume that it stays, let's forget about that at -3 and just focus on the slope. So the slope now starts to decrease by 20 decibels per decade because this is a pole. It's a cutoff frequency of a pole, which means that from now, every time we increase the frequency by a factor of 10 with respect to this frequency, the Bode plot decays by 20 decibels, goes down by 20 decibels. So we can keep going now, and if you keep going, we have another cutoff frequency here. So we have to stop at this cutoff frequency and then reassess the problem here, because 10 to the power of 0 is 1, and that's the cutoff frequency of a 0. So what is the magnitude of the Bode plot at 10 to the power of 1? If here we are at 20, we move on by 10, and that gives now a slope that it decays at a rate of -20 dB per decade. And now at 10 times this frequency, we reach 0 dB. Is this clear?
Yes.
Yeah.
Professor, what did you do? Did you do anything about the 17 dB? Like
No, I'm neglecting that for now.
Oh, okay.
Yeah. So if we consider the -7 and the -3, then here we would be at -7 at 17, and then here would be at 17 minus 20 would be -3. Let's forget about that at 3 for now and just focus on the slope. So when you reach 10 to the power of 0, that's another cutoff frequency, and this is now a 0. What does the 0 do to the Bode plot?
Makes the slope 0.
It will make the slope 0. But what it actually does, in this particular case, it makes the slope 0. But to avoid confusion, it adds 20 decibels per decade to the existing slope. It does not make the slope 20 decibels per decade. It does not make the slope 0. It adds 20 decibels per decade. But because we have something that is already decreasing by 20 decibels per decade, plus 20 decibels per decade will make that 0. So now the slope will change to 0, and we'll continue on until the next cutoff frequency. Because now we reached a pole, reached a 0 at 1 radians per second. We had the slope of -20 decibels per decade. The 0 adds 20 decibels per decade past its cutoff frequency, and now it becomes 0 decibels per decade. Yeah?
Or you can think about like if it is only S and then there will be like no change for the slope.
For now on, the slope
no.
is constant. The slope has
yeah.
changed because we added a 0 to it.
And
And then we can keep going now towards the higher frequencies. But as we do that, we cross another one here that's 10 to the power of 1, which is 10. That's the cutoff frequency of this pole here, and it's squared. So there are 2 poles at 10 to the power of 1. What happens?
it will increase 20 dB.
It will decrease because it's a pole. Right?
40
It's a pole.
dB a decade?
It will decay by 40 dB. So each pole, like this one here, changed the slope or added to the slope -20 decibels per decade. There are 2 poles at the same location, each adds -20 dB. Now we start to decay by 40 dB per decade. So what is the magnitude at 10 to the power of 2, which is 10 times our current frequency?
-40.
-40. And at 10 to the power of 3, which is 10 times that frequency, it would be -80. So this slope is now negative 40 dB per decade.
Professor, could you please explain the negative 40 part? Like, where did that come from?
Yeah, so this one here, this negative 20 came from this pole, right? One pole added negative 20 decibels per decade. If we now pass that pole, we have a slope of 0 here, and when we reach this point, there are these two poles at 10. Each of them adds negative 20, the same way this one did, but they happen to be at the same frequency, so minus 20 is negative 40.
Oh, okay, thank you.
Now let's look at the phase. The phase at a low frequencies is only affected by this gain. The gain of a phase is 0. And the gain of a constant, so what I'm saying. The phase of a gain, the phase of a gain is 0. The phase of a constant gain is 0. So it goes from 0 all the way to 10 to the power of negative 1, where we encounter one pole. What happens to the phase? The pole adds negative 90 degrees to the phase. So at this point, the phase goes to negative 90 degrees because this is a pole right here. And we'll continue at negative 90 degrees up to the next cutoff frequency. The next cutoff frequency is a 0. What happens to the phase? What does a 0 do to the phase? If a pole adds negative 90 degrees, the 0 adds plus 90 degrees, right? We have a same slope with negative 20 decibels per decade added by the pole. The 0 added 20 dB. The pole adds negative 90. The 0 adds plus 90. So we go back to 0. And we continue up to the next cutoff frequency. This next cutoff frequency is a pole. Is actually two poles at the same cutoff frequency. What happens to the phase?
Minus 180.
Minus 180, exactly. Each pole adds negative 9. And the phase now goes all the way down to negative 180. We can now try to do some nice interpolation here. This would be 45, negative 45, and halfway here would be 90. And that would be the phase of the transfer function. Okay, notice again, the critical point here in our analysis is this point where we had two poles, double the slope, double the phase. If you had two zeros, double the slope, double the phase, but now it would go upwards and this would also jump up. Let's put in a square here. What happens?
It will going up.
Go back to 20.
Up to this point, nothing changes, but now we encounter two zeros at once. So we add 40 dB to a existing slope of negative 20 dB. So it now goes up by 20. And what happens next? Now we are at 10 radians per second, two zeros. What happens to the slope? Two poles, excuse me, two poles. What happens to the slope?
The slope will just become negative 20 dB per decade.
Exactly. The slope
together.
that is now 20 is we add negative 40 to it. It becomes negative 20. And here we go back to 0, and here we are at negative 20 now. What happens to the phase? Up to this point, nothing changes. But now here we are at negative 90. We have two poles, each adds 90 degrees. We go from negative 90 all the way up to 90. Stay at 90 and then go back to negative 90 once we reach the double pole. Okay, I don't have space here. I'm gonna mess everything up if I attempt to draw it. Are we good?
Yeah, I think I some kind of got it. I need to think about later, but I think I think I got it. Thank you.
Sounds good. Anybody else has questions? No? Okay. So you see, this is a lot faster. We can just do the entire thing at once instead of just going one by one and then adding all of it. That's exactly what we did. It's just that we thought about the addition before we drew the Bode plot.
So for the graph, we don't consider like the -3 decibels.
Oh yeah, so if we consider the -3 decibels, we should, but I mean, for our purposes, that is enough to just do it this way. So if we consider the -3 decibels, so here would be a -17, here would be a -3, here would be at -3 minus 3 minus 3, so -9, right? 2, -3 for each pole, and then everything from there would start at -9, it would go -40, so -49, and -40, -89. It just shifts from the point where when you reach that, everything shifts down by negative. Okay. Let's do another one I have here. The -3, of course, this is an approximation. So the -3, we can ignore it, but if you plot this with MATLAB, you just do Bode of that function, it will be shifted. So you see that at this point here, it will be actually a -89. And this discrepancy is because, no, this is, of course, an approximation. We don't need to worry about that. But we should need to be aware that that exists. Okay, let's do this now. And this one is a bit different because there is a pole at the origin of the S-plane here. So what do we do with this one? If you go down to the low frequencies, that pole is actually affecting the low frequencies as well. So that's a problem. Just erase this, and then scratch here. What happened yesterday? The cleaning robot entered the room, dropped this thing, and as it dropped, it created this big scratch. So that's going to stay there now. Can't get rid of it. Okay, let's just do this function, and then you're going to move on to complex poles and zeros. But you see, it's not very complicated. And again, if you want to check your answers, just type Bode of the function, and that will give you the exact Bode plot. What do we draw here are, of course, approximations of the actual Bode plot. Okay, so what do we do with this one? This doesn't display very well. What do we do with this one? Now, this one is a bit different because you have a gain, we have a pole at the origin, and you have a cutoff frequency at 1 radians per second from another pole. So you have, again, 3 elements. If you now go to the low frequencies, what is happening? This pole at the origin is affecting the Bode plot everywhere. It doesn't have a cutoff frequency, it's at 0. And it is located at 0. So it will affect the Bode plot everywhere. We need to account for that. Then you also have a gain of 5. That one you can already calculate. 20 log of 5 is about 14 dB. Now let's look at this problem. We have this gain and we have that. So if you only had 1 over S, how would that look like here? 1 over S would be 0 at 1 radians per second. right? Would be 0 at 1 radians per second. And what would that be at 0.1? It's a pole at the origin. So there is a slope of negative 20 decibels per frequency decay. So if you go down, go back by a factor of 10, it goes up by 20. So if you only had this, we remember that the pole at the origin always passes by 0. So this is 1 over j omega, which is the same as whose magnitude is 1 over omega. 20 log of 1 over omega is the same as negative 20 log of omega. So that's the slope of negative 20 per frequency decay. When omega is 0, is 1, then this gives 0. So at 1, we pass by 0. At a negative 0.1, we should be at 20, and the 0.01 should be at 40. So we should be at the first frequency we have, we should be at negative, we should be at 20 decibels if you only consider this. But also there is a gain. The gain adds 14 dB. So that shifts everything up by 14 dB, and we are actually at 34. So we are actually starting over there. Any questions here before we proceed? We continue. Let me repeat what I did. If you only had 1 over s, 1 over s passes by 0 dB at 1. So here it should be negative 20, here it should be negative 40, which means that here we should be at plus 20. But there is also a gain affecting. So everything shifts up, and instead of 20, we will start at 20 plus 10, plus 14, which is 34. Are we good? This is clear. Because everything else will start from that point. So
Yeah,
yeah.
and it will shift for all the others.
Yeah, the shifts everything upwards.
Okay.
Okay, so we are starting here. Now,
Sorry. Excuse me, Professor.
Yeah.
I'm so sorry. Do you mind like starting the question again? Like my Wi-Fi was cutting out, so I could barely hear what you were saying.
sorry, could you repeat the question? There's some background noise I couldn't understand.
Oh yeah, sorry. Do you mind starting the question again? My Wi-Fi kept cutting out, so I could barely hear what you were saying. Like the only thing I know or I heard you say was you find 20 of log 5, which was the gain, and that was 14 dB. Why didn't you hear anything else?
So we are dealing with starting at the low frequencies, and the low simply 5 over s, because we haven't reached this pole, right? So we have the gain 5 that is affecting the entire Bode plot at all frequencies, and also have 1 over s that is affecting the Bode plot at all frequencies. If you look at a 1 over s, that's a continuous slope of negative 20 decibels per decade throughout the entire frequency range. And we know that 1 over s will pass by 0 at 1 radians per second. It will then be negative 20 at 10, and you'll be negative 40 at 100, which means that if you go now back at 0.1, we should be at 20 dB. So we should start here, but there is this gain 5. 20 log of 5 is 14 plus 14. So we shift everything up. So instead of 20, we start at 34. Okay, so we are basically taking this curve that comes from 1 over s, adding 5 or 14 dB to it, everything shifts up. So we're starting at 34. Now let's move on. So we're starting at 34. If you go now by moved by frequency by a factor of 10, we go down by 20. So where should we be at 10 to the power of 0, or at 1 radians per second?
14.
14. Exactly. So here we should be at 14. Now go down by negative 20 dB, and you go to 14. And again, if you look now at 14, if we didn't have the gain here, we would indeed be at 0, but the gain is shifting everything upwards. 14. This is 14. What happens now? Well, now we reached another cutoff frequency coming from this pole, and this pole will add negative 20 decibels per decade to an existing slope of negative 20 decibels per decade. Where should we be then at 10 to the power of 1?
Minus 20,
Minus
40 dB.
six.
Minus 26. Yeah, so we now start to shift the slope. And that's now negative 40. So we go down by 40 dB. 14 minus 20 is negative 26. Around here.
But there's only one pole, so why is it negative 40 and not negative 20?
So up to this point, there was one pole. Past this point, there is another pole at 1. Each pole contributes with negative 20 dB. The pole doesn't make the slope 20 decibels per decade. It adds to that. It adds to the existing slope. The existing slope was negative 20. We passed by another pole. It's adding another negative 20, and now the slope becomes negative 40.
Okay, so because of the pole at the origin, it was sloping at by 20. So if there wasn't the other one at 1, it would have continued.
Yeah.
But then because that one is there, it adds another 20. So it's, the
Correct.
slope increased.
Correct. The slope
Okay,
is now negative 40.
And is there a particular reason you didn't start at the y-axis, or
At the y,
like,
no,
okay.
Just the first frequency is here.
Okay, thank you.
And now we can keep going. The next frequency would be 10 to the power of 2. That is then minus 26 minus 40. Would just keep going and would be negative 66. Let's look at the phase. Where does the phase start? Where does the phase start? A low frequency is what is acting on the system. This and that. Number 5, the gain is a phase of 0, but the pole at the origin adds negative 90 degrees everywhere on the Bode plot. So we should start at negative 90 degrees. And that goes, it remains 90 up to the next cutoff frequency. What happens here? We cross another pole. That pole adds negative 90. Oops. So we go down to now negative 180. And if we interpolate this, it should have a smooth curve passing by negative 135 right in the middle. If this was squared, what would be the difference? This slope would become negative 60, right? Negative 20 minus 40 for the 2 poles there, if this was squared. And the phase would go down to negative 270 degrees. If this was actually a 0, what would happen to the slope? If we had 5 times s plus 1 of this, what would happen to the Bode plot?
The slope would be 0.
The slope here would become 0. And we just keep going like that. And the phase would shift to 0 at this point, and it would have something like that.
Professor, last class, when we're dealing with poles on the real axis, you said that when W equals W naught, the phase was negative 45.
Yes.
So how come like we increased from negative 90 to 180? That's like a jump of 90. Why not 45?
Well, no, but we are passing by negative 45. You see, we are here at negative 90 because of the pole that we had at the origin. And then the next pole is adding negative 90 degrees, precisely at its cutoff frequency. It is indeed adding negative 45 because we are at halfway through a negative 135. right? So the pole doesn't, once again, the pole does not make the phase and the slope -20 and -90. It adds to whatever we already have. All right, so we were at -90. We crossed the pole. The pole now made the phase -180 at its cutoff frequency exactly. It just added -45 exactly as we had in the next lecture. Right, but we had that pole isolated here. That pole contributes to something that already exists.
Can you explain why we start at -90 again?
That's a pole of the origin, and the pole of the origin has always a phase at -90 degrees. So if the pole of the origin is 1/s, which is -1, let me do this step by step. 1/s is equals to 1/j omega, multiply this by j. This is the same as -j times 1/omega. If you plot this imaginary and the real part is 0, imaginary part is -1/omega. So here is the vector, this is the angle. It's always -90 degrees for all frequencies. If this was a pole, it was a 0, it would be shifted upwards and it would be +90 degrees. The last lecture. So that affects, you see, this is for all frequencies, so affects the Bode plot everywhere. Okay, only works for a pole at the origin. Okay, so let me erase this, and then now let's jump into complex poles and zeros. You will see that it's very similar to what we just did here. You notice in this slide, now we are dealing with complex poles and zeros. We have to go back to the standard form of a second order transfer function, which is omega 0 squared divided by s squared plus 2 zeta omega n s plus omega n squared. And you're going to use that. So this is valid, of course, because it's complex. Zeta needs to be less than 1. Otherwise, we would have real poles and zeros. And then you can just go back to what we just did. Okay, so there's some math involved here. But this is something we can check later. It's just a basic math manipulation of complex variables. So if we are now zeros, this is the standard form we're going to use, similar to what we did before. And this is now the case for zeta smaller than 1. We have complex poles and zeros. If you take this transfer function and now divide every element in the transfer function in the numerator and denominator by omega 0 squared, we can rewrite that expression as follows. And you see here is the same expression, just divided everything by omega 0 squared. And this is now the cutoff frequency. We'll show here and we'll show there, +1. So whenever we need to use this, we have to prepare the transfer function in this form. The denominator needs to be s squared divided by omega 0 squared plus 2 zeta s divided by omega 0 plus 1. And omega 0 is the cutoff frequency of this particular complex pole. When you replace s with j omega, we can do now the same procedure we did in the last lecture. Replace s with the j omega. Here and there. And now isolate the real and the imaginary part. So here we have the real part of this pole. Here we have the imaginary part of this pole. If you want to get rid of the complex variable in the denominator, just multiply it by its complex conjugate. That's what you're doing in equation 3. You see the negative sign in the imaginary part. And now in equation 4, we can follow the steps later. In equation 4, we have the same expression we started with, but now we highlight the real and the imaginary part. The first term is the real part, the second term is the imaginary part. If you want to calculate the magnitude of this transfer function, just take the square root of the real part squared plus the imaginary part squared. If you want to calculate the phase, arctangent of the imaginary divided by the real. And that's precisely what we're going to do. But let's do this in steps. As we did for the complex, for the real pole and the real zero, we need to consider 3 cases. So the first case is when the frequency we are evaluating the system at is much smaller than the cutoff frequency. If this is the case, then when you calculate omega divided by omega zero, this tends to 0. We are to the left of the cutoff frequency, and this condition applies. When you do that, this entire transfer function simplifies to something very simple. You can follow the steps later, it's just basic math. But under the assumption that omega is much smaller than omega zero, this whole thing simplifies to 1 plus 0j. So clearly from this, we can see that the magnitude would be 1 or 20 log of 1, 0 decibels, and the phase would be 0 degrees. You only have a real part. So if you now plot real and imaginary, we are simply here. And the phase of this is 0. So in case 1, up to the cutoff frequency, the magnitude of the transfer function, would be 0, and the phase would also be 0. Exactly the same as for the real pole. Up to the cutoff frequency, nothing changes. Now let's consider the next case. Next case is the opposite. We passed the cutoff frequency. You are to the right of the cutoff frequency. And then the frequency we are evaluating the system at is much greater than the cutoff frequency of the system itself. We can apply the same method. For example, here, if you make that assumption, we can say that 1 minus omega divided by omega 0 squared. If omega is much greater than omega 0, we can neglect that at number 1, and you can say that this is approximately negative omega divided by omega squared, right? Because it's much greater than 1. So this is the type of simplification we can do now. And by applying this condition, the entire transfer function simplifies to this. And again, we see the real and the imaginary parts. We can calculate the magnitude of the transfer function, real part squared plus imaginary part squared. Second last equation. And you have, after all the manipulation there, you can try to do that on your own later. We have 20 log of omega divided by omega 0 to the power of negative 2. Property of the log function is that this can travel now to the front. And the final result is that past the cutoff frequency, the magnitude of the transfer function is negative 40 log of omega divided by omega 0. What was this magnitude for the real pole? You remember what we had for the real pole was G equals to negative 20 log of omega divided by omega 0. This was for the real pole. This is for the complex pole. Do you see any differences here? Well, it's just 2 times the real pole. The slope past the cutoff frequency now will decrease by a factor of negative 40 decibels per decade. In the case of the real pole, the gain was 0 up to the cutoff frequency. Past the cutoff frequency would have a slope of negative 20 dB per decade. For the complex pole, same thing, but the slope past the cutoff frequency is negative 40 dB per decade. So this is precisely the same as having 2 poles at the same cutoff frequency, 2 real poles at the same cutoff frequency, as we did in the example earlier. The slope is now twice the slope of a real pole. We'll summarize this later, but we still have one condition left. So here's the visual representation of that. So up to the cutoff frequency, we had a gain of 0. And when you reach the cutoff frequency here, which is omega 0, every time now we increase the frequency by a factor of 10. the slope decreases by negative 40 dB. For the real pole, it was negative 20. For the complex pole, is negative 40, which is the same as having two real poles at the same cutoff frequency. And let's see if that is indeed the case. Let's look at the phase. The phase, we can simply calculate by taking the inverse tangent of this divided by that. And now, because you are increasing the frequency, we can make the frequency tend to infinity. And when that is the case, the part inside here, the transfer function or the inverse tangent will tend to 0. And the inverse tangent of that would be negative 180 degrees. In fact, the inverse tangent of 0 would be 0. Well, why is that negative 190 degrees instead? Well, we can take the real and the imaginary parts of the transfer function here and plot it. And if you plot it there, we'll see that the transfer function phase will always be in the third quadrant. And as the frequency tends to 0, both of these parts will shrink to 0, but they go to 0 like that, and they reach 0 from the negative 180 degrees, not from 0. Right? So interestingly, again, the phase past the cutoff frequency is subjected to a shift of negative 180 degrees, which is precisely twice the amount of phase shift we had for a real pole, or when you calculated it. Right? So the slope compared to a real pole doubles, so does the phase. So having a complex pole, once again, is equivalent to having two real poles at the same frequency. The slope goes to negative 40 past the cutoff frequency, phase goes to negative 180 past the cutoff frequency. Before the cutoff frequency, it's 0. We still have this third case, and here is the only difference compared to two poles at the origin, two real poles. The third case is when we are precisely at the cutoff frequency. When you are precisely at the cutoff frequency, omega equals to omega 0, and you can now simplify the entire transfer function by just applying that condition. And under that condition, this is what we get. This is a simplification, assuming omega equals to omega 0. We can do now 20 log of the square plus the real part squared. And this is what we get. We get something that is now a function of the damping ratio. At omega equals to omega 0, the magnitude of the transfer function is negative 20 log of 2 zeta of the damping ratio. So now, depending on the value of the damping ratio, we'll see a bump or a decay at this specific frequency. So when zeta is precisely 0.5, we have 2 times 0.5, that's 1, 20 log of 1 is 0. So when zeta is 0.5, at the cutoff frequency, we have 0 dB. If zeta is smaller than 0.5, then what happens? Then you have a negative 20 log of something that is less than 1, smaller than 1, which is a negative number. And you have a negative number in front of it, so you end up with a positive number. So when zeta is smaller than 0.5, the result of this operation is a positive number, and the Bode plot now goes up instead of going down. Just a little bump at that specific frequency before it takes its slope of negative 40 dB per decade. If zeta is now greater than 0.5, then 2 times something greater than 0.5 is greater than 0, is greater than 1, excuse me, is greater than 1. 20 log of something greater than 1 is a positive number. Because of this negative sign, the result of the operation is negative, which means that at the cutoff frequency, the Bode plot will decrease by a certain amount, 20 log, negative 20 log of 2 zeta. And when zeta is 0, then you have 20 log of 0, that tends to infinity. Okay, so here is the only difference compared to having two poles at the same frequency. Here's what happens precisely at the cutoff frequency. And at the cutoff frequency, we now need to evaluate this. The Bode plot may go up or may go down, depending on the value of zeta. Zeta greater than 0.5 makes the Bode plot go down. Greater is smaller than 0.5 makes the Bode plot go up at the cutoff frequency. And everywhere else, we have precisely the same effect as having two real poles at that specific cutoff frequency. We can look at the phase. In the phase, we can easily calculate the phase as well. And the phase turns out to be negative 90 degrees, which is halfway between 0 and negative 180. So here is the main summary of all this. For a complex pole, before we reach the cutoff frequency, phase and magnitude are both 0. Once we pass the cutoff frequency, the magnitude decays by 20 dB per decade, the phase goes to negative 180. Precisely at the cutoff frequency, the phase is negative 90, and the magnitude is negative 20 log of 2 zeta, which may go up or may go down. So with the exception of what happens at the cutoff frequency, this is analogous to having two equal real poles, or two real poles at omega 0. Okay. So this is for the pole. If we had a 0, everything shifts. Instead of having negative 40, we have plus 40. Instead of having negative 180, we have plus 180. And instead of having negative 20 log of 2 zeta, we have positive 20 log of 2 zeta. Instead of having 90, we have plus 90. For the complex 0, it's exactly the same, just mirrored with respect to the real axis. Are there any questions before we do an example? No? Okay, so if there are no, here is the, again, a summary. You can see the Bode plot exactly like the one we had for the real pole, just the slope and the phase have shifted. And what happens at this point will depend on the damping ratio. Here, so this is for that specific transfer function, and I'm varying the damping ratio from 0.1 to 0.9. And you see now these bumps that occur when the damping ratio is smaller than 0.5. Right, so the damping ratio, as we saw before, is something that can be an indication of how much energy is being dissipated in the system. When there's little energy being dissipated in the system, we can see here that at some points the magnitude will increase by a lot. And when there's a lot of energy dissipated in the system, and the magnitude decreases at that omega 0. So here we can see some effects of resonance. And when you reach a certain resonance, we see that the magnitude may increase significantly. There is this, I don't know if you guys heard of, there was a bridge back in the 60s that was built, and then they had troops marching over the bridge. And when they were walking on the bridge, they had to stop marching, because if they were marching, the frequency of excitation from walking on the bridge would match the resonance frequency of the bridge, which would be, in this case here, 1 radians per second, 1 radians per second. And then the displacement of the bridge would exponentially increase because it didn't have enough damping to dissipate that energy. And it happens that the characteristics of the transfer function of the bridge had a transfer function that had a cutoff frequency very close to the frequency one would induce when walking on the bridge. And the bridge could potentially collapse. And there is another example where wind just destroyed a bridge. You can Google, go to YouTube and just type resonance frequency of a bridge, and you see a very long bridge that collapsed because of wind, not because of the speed of or the intensity of the wind, but because the wind created a input excitation that was too close to the resonance frequency of that bridge. So the wind was some sort of a cyclic, and the frequency of the wind displacement induced in the bridge was too close to its resonance frequency. So the resulting displacement of the bridge was a lot higher than what we would give as an input, and the bridge eventually collapsed. You can see the video online. This is black and white, is an old one. Okay, and in both cases, the damping ratio of the transfer function that characterized the system was smaller than 0.5. Not enough damping results in an output displacement greater than the input displacement, right? A gain greater than 0 decibels. If we had enough damping, it would be the opposite. The output would have a smaller magnitude than the input, and that's what we would expect from something like a bridge, right? But precisely at the cutoff frequency, it collapsed. Okay, so let's, are there any questions? Any questions? No? Is anybody still there? 38, okay, good. All right, so let's do this example here. We have this transfer function, and we want to calculate we want to draw the Bode plot. Let me just move this Bode plot out of the way. Okay, so if you calculate the damping ratio of this transfer function, you will see that the damping ratio will be smaller than 1, which means that you cannot split this denominator into 2 real poles. We have to deal with the complex poles. If you're dealing with complex pole, we need to now prepare the transfer function in the standard form. And the standard form is 1 over s divided by omega 0 all squared plus 2 zeta s divided by omega 0 plus 1. How can you do that? Well, we can divide everything, the top and the bottom of the equation here, by omega 0 squared, which is 2. By omega 0 squared, which is 4. So omega 0 will be 2. And when you do that, when you divide everything by 4, so 4 divided by 4 is 1. We have s divided by 2 squared. So, all right, so 4 here as well, plus 0.2 s plus 1. Okay. So omega 0 is clearly 2 from this, but now here we have a number 4. So what do? We can divide the top and the bottom by 2. And we can rewrite this as 1 over s over 2 squared plus 0.2 s over 2 plus 1. Why I'm keeping this over 2 here? Because this is the standard form, right? We need to make omega 0 show there and here as well. So here they are, right? So omega 0 is visible is 2 radians per second. That's the cutoff frequency. Are we good here? Any questions here?
Sorry, Professor, in the function, it is 2 zeta s over omega 0.
Yeah, so here is 2 zeta. 2 zeta equals to 0.2.
Okay, thanks.
Now this is the best zeta I have drawn so far. So this is zeta, and I already changed it, 0.1. All right, 2 zeta equals to this, zeta equals to 0.1. So zeta is smaller than 0.5, which means that at the cutoff frequency of 2 radians per second, we should see an increase in the Bode plot magnitude. And what is that? Well, we can calculate that. That is negative 20 log of 2 zeta. So negative 20 log of 0.2, that is plus 14 dB. So this is omega equals to omega 0. Right? At the cutoff frequency, as we saw before, we need to pay particular attention to that because now the Bode plot may go up and or down depending on the value of zeta. And that is always negative 20 log of 2 zeta, negative 20 log of 0.2 is approximately plus 14 dB. That will occur at the cutoff frequency. And what is our cutoff frequency in this case? 2 radians per second, right? Here's omega 0 here and there. So we should be, so this is 1 is a log scale, so it should be approximately here. Okay, so what happens to the Bode plot? If you go to the low frequencies, what do we have? We have only a gain. The gain is 1. 20 log of 1 is 0. So the Bode plot, it starts at 0. And it stays at 0 up to the cutoff frequency, which is about around here. That's 2 radians per second. And what happens there? What happens at 2 radians per second? Now, at 2 radians per second, which is the cutoff frequency, the Bode plot needs to go up now by 14 dB. That this is not as low, it's just the actual magnitude. So it needs to bump up to, oh, that's too much. It will go up by 14 dB. This magnitude here is plus 14 dB compared to what we had before, right? Because here is 0, we go to 14, which is this point. If this was 10, then the Bode plot would start at 20, and at this point it would jump up 14, would go to 34, right? But we are starting at 3. Okay, and then past now the cutoff frequency of 2 radians per second, what happens to the Bode plot? We come back to 0, and now the Bode plot, it gets a slope of negative 40 dB per decade. So from 2 to the next cutoff frequency, which is not next cutoff frequency, to the next decade is a factor of 10. We go to 20, and this now gives a magnitude of negative 40 dB, because you're now going down at a rate of negative 40 dB per decade. Why 40? Because it's a complex pole. It's a complex pole. So from 0 at frequency of 2, when you go to 20, it was a factor of 10 in frequency. Bode plot goes down by 40. Right? And this is 10, which is 1 decade. What is the magnitude at 200 radians per second?
It is still negative 40 dB.
The slope is negative 40 dB, but the magnitude itself is negative
minus
80. Yeah, negative 80. Negative 40. Okay. Phase. What happens to the phase? Well, the phase is easy. You only have one complex pole. So the phase goes from 0 to negative 180 at the cutoff frequency. And you can now try to interpolate this And it should pass by negative 180, no, sorry, negative 90, right in the middle.
So I just have a quick question about the cutoff frequency behavior. So at the cutoff frequency, we have our bump, but we have to, we will return from the effects of the bump before we head into the effect of the negative 40 dB per decade, right?
Right.
Okay.
Yeah.
So
Yeah,
it doesn't-
otherwise, then the slope would go to start here, and everything would be shifted by 14. Right?
Okay.
Yeah,
But
so it comes
not,
back.
that's not the case though. It won't start at the 14 dB point.
Now it comes back to where it was before the bump.
Okay, great. Thank you.
Professor, so if here the zeta is like bigger than 0.5 and then there's no bump.
If this data is bigger than 0.5, then this would be a negative number. And then we would
Okay.
already start to decay before that, like that. And then this shift here would be negative 40.
Yeah, then
And
there
then
is
we
no
take this
bump
one.
anymore.
Yeah.
Okay.
Yeah. So the bump only occurs when zeta is indeed greater than 0.5. Okay. Any questions?
Which point is the bump starting on this graph? Is it 1 rad per second?
2. Well, where exactly it starts, we can't tell.
Okay.
Yeah. So typically the smaller zeta, the sharper it is here, and the sharper this change will also be. So the change will be more sudden. But where exactly it starts, I don't know.
Oh, Professor, just one more question. So it will reach to the peak at the frequency of 2?
It will reach the peak at the frequency of 2. Yeah.
Okay, got it. Thank you.
Yeah, this how wide this transition is, for example, it depends on zeta. So one rule is this should be around omega 0 times 5 exponential of minus zeta, and omega 0 5 times 5 exponential of zeta. So these are empirical observations. It's just that the smaller zeta, the sharper these transitions are.
So how do we figure out for like assignment questions and exam questions how wide that bump is? At what point do we start moving into the negative 40 dB per decade slope?
I don't know. No, we have. I don't know. I don't know how to do that. It's really something that we need to use MATLAB for. I would say a good indication is if this 14 dB is a lot. This needs to be relatively sharp. If you go to the example I had, where did it go? Here. Now you see that this thing, it becomes sharper and sharper, especially in the transition in the phase. You can see that it's a more sudden change. But where exactly it starts, it's hard to tell. We can tell for the frequency. The frequency is here. You see what I was just saying? Omega 0 times 5 is the exponential of negative zeta and the plus zeta. That gives you an indication of the phase. But for the magnitude, yeah, I don't know.
Okay, so we just have to approximate it ourselves. Yeah. Okay, got it. Thank you.
And if you want to confirm this, again, just define your function g of s as a function of s, and then do Bode G in MATLAB, and then we'll plot the Bode plot for you.
Professor, just one more question. So how about the situation zeta equals to 0? So that point will go to the infinity?
Yes, then it goes to infinity.
Okay, got it. Thank you.
There would be a system with no damping at all, right? No damping at all. So in some cases, for example, You guys heard of piezoelectric actuators before? It's a crystal, like a material like this, and you apply a voltage to it. And when you apply a voltage, it will change shape. It will expand or contract, depending on the frequency, depending on the sign. And it can also work the other way. If you move this, if you hit it with a hammer, for example, and you put a multimeter here, you will see a voltage showing up. This is typically the sort of actuation system that is in camera lenses, for example. It's a piezoelectric actuator that deforms, and then it makes something rotate. So clearly here, we want to work very close to the resonance frequency, and we want a damping ratio that is the smallest possible. Why? Because we want to maximize the output displacement. We want to be operating close to this peak here. The input to the system would be a voltage, and the output would be the displacement of the piezoelectric actuator, of this kind of ceramic material. And if you're using this to create motion, of course, we want to operate around here, because in that case, let's say 1 volt would create a change of 14 dB. That would create how much would that be in a factor of, would be a factor around 5 times higher. So if you put a 1 volt here, you get a factor of 5 times the output. If you're now operating on this point here, the magnitude decreases significantly. So when you put a 1 volt, you see almost no displacement. Right? But when you operate close to the resonance frequency, then a small voltage input creates a large displacement. In this particular case, we do want to operate near the resonance frequency, near the top of the bump here, and we want a damping ratio that is very close to 0. We can't achieve 0, but we can get close to it. In other cases, such as the bridge, we want to be operating far from this point. We want to be operating over here. A small input to the bridge, displacement input or force input, would create a small displacement because the gain is very small. Right? It's negative dB. It's a very small gain. If you operate right there, then a small input creates a large displacement, and the bridge may collapse. In this case here, that's precisely what we want. We are creating motion from a voltage input.